Card. Got it. Share screen. Okay. Oh, this is not what I wanted. Don't see. Okay. Can you guys see my screen?
Yep.
Yes.
Very cool. Awesome. Okay, so any questions on the previous chapter regarding gases, liquids, and solids? We essentially just pretty much eliminated liquids and solids. So any questions on gases, on the different kinds of laws?
None here. It's a lot to take in. So
Yeah, I was rewatching it all. So if I have any questions, I'll just send you an email on it.
Please do. Yeah, so let's make sure that you guys are I know that was a lot of content, and so try my best to not make it more complicated, because technically I had to cover that chapter, which we did not. So try to do the best I could to help you guys. So so I would encourage you guys to watch that recording and a re-recording, and if you have any questions, please look me up. Cool. Okay. And then Brian, I don't know if you saw, but your grades, final grades, sorry, not final grades, midterm grades have been posted.
Okay.
So I'd encourage you to look at that solution. If you have any questions, if you don't agree with the grading, or if something doesn't make sense, please reach out and we can talk about it.
Okay.
And just a friendly reminder, there's still some pending assignments for you, so please get to it as soon as possible. I greatly appreciate that.
Okay.
Cool. Awesome. Okay, so if you guys don't have any other specific questions, then let me get started with the new topic. And today we're going to be covering solutions. Okay, and solutions is actually a pretty simple and interesting topic. So we'll go through some of the concepts, the general concepts we're going to be covering in this chapter. So we're going to be defining a solution, a colloid, and a suspension. Okay, there are all kinds. So basically, it is nothing but a solid plus liquid mixed together. That's what a solution is. And the solid can sometimes be replaced by gas. Okay, but this liquid is called as solvent. So there are two things that you have to keep in mind when you're looking at solution. One is called as the solute, the thing that is dissolved, and the solvent, the one that dissolves or that hosts the solute. Okay, the solute can be usually a gas. Sometimes the solute itself can be a liquid, and of course, the most common one is solid, and the solvent is invariably a liquid, invariably. Okay, because when it comes to gas and gas, it's not called a solution, it is called as a mixture. So these two together form as what you call as a solution, right? Okay, so we're going to define the basic definition of a mixture in the form of solution, then colloid and suspension. We'll define electrolyte and non-electrolyte. This is very important for battery cells, circuits, medical field, so many different things. And non-electrolyte, electrolyte is something that conducts electricity. Non-electrolyte is something that does not conduct electricity. Okay. Then we are going to be learning the concept of solubility. How much a substance dissolves in another. Okay, so that's called as solubility. Then we are going to be talking, like in the last chapter, we talked about temperature and pressure as two important parameters along with volume. Okay, so if you recall the beginning part of chapter, I can't remember the chapter number, the previous one, gases. We called gases as compressible fluids. Okay, something that you can press and it changes its shape. Liquids are incompressible fluids. Okay. So that's why for liquids, volume is not that critical of a pressure parameter as temperature and pressure. Okay. So we are going to see that if you raise the temperature, decrease the temperature, increase the pressure, decrease the pressure, what effect does it have on the solubility? Then we are going to be spending a lot of time to define the concentration term. We already saw that concentration is indicated by these square brackets, and the units are usually moles per liter. This is the same thing as, in some way, it is also similar to density. Density is type of a concentration, because density, the units are kg per meter cube. The concentration is nothing but, in a given volume, how many moles or how much substance of that material is there. Okay, so if you're talking of a lemon concentrate, right? Okay, so this is lemon concentrate. Obviously, the word concentrate indicates that it is very strong, right? So if you want to make a lemonade, you're not going to be drinking directly from this lemon concentrate, will you? Would that make sense?
Yep.
Yeah.
Okay, yeah. Did someone say yes?
Yeah, we both said yes.
No, would you drink from the lemon concentrate directly, that small green bottle?
I mean, I like sour things, so yeah. But no, you would dissolve it first in water.
Why? Exactly. Okay, you like sour things? No problem with that. But generally, I mean, you're trying to fix yourself a lemonade. You understand where I'm going with this, right? You wouldn't drink directly from the concentrate, right? Why? Because it is too concentrated, correct? Is that fair? And what you're doing when you're adding water to it to make lemonade, you're diluting it, correct?
Yeah.
Make sense? So that's the concept of concentration, right? I mean, anything that is concentrated, you don't want to generally deal with it. But at the same time, I mean, you like, like the concentrate, usually you take 1 teaspoon and then you dilute it in like 8 ounces of water. That gives you a decent lemonade. You add some sugar to it and then you're happy, right? But if you add 1 teaspoon and of the concentrate, and then you put like an entire jug, 32 ounces, then you're going to be complaining, well, this is too dilute. It's not tasting like lemonade, right? And again, I'm not trying to, everyone has their subjective relative preferences in terms of how sour or sweet or whatever they like. But generally speaking, you like to operate within an optimum range. But if you just keep on diluting it too much, it's not going to give you the effect of wanting to drink or fulfill your desire to have a lemonade, right? It becomes just water with just a tinge of lemon concentrate in it, and you would say that it is too dilute. So where I'm going with this is, in everyday life, we talk about concentration, correct? And concentration is nothing but that kg, or in this case, it is milliliters of the solute, which is what you're dissolving in that solvent, or in this case, the solution. And so this becomes the lemon concentrate. This becomes the water plus the lemon concentrate. Together, they form the solution. The water here is the solvent, and the lemon concentrate added to it. That combined mixture becomes the solution. And the lemon concentrate, you express how much quantity of that, either in milliliters or kg or moles, and that is what you call as defined as the concentration of the solution. And in the previous chapter, we saw that concentration is generally expressed by this square brackets. So if I say 10 moles per liter, so it has 10 moles of the substance that is dissolved in 1 liter of the solution. Okay, so that is one of the chapter objectives. And then we are going to be seeing, if you if you change the dissolved particles in the solution, how does that change the boiling point and the temperature and the melting point? And if time permits, on Thursday, we will try to do some practical application in terms of osmosis and reverse osmosis, which is one of the most common ways of water purification. And then this is the working principle of dialysis, which is what, unfortunately, some people have to rely on dialysis if their kidneys are not working. You know that the kidneys are basically purifying organs of the body. They kind of remove the impurities. But if your kidneys start failing, or if they're not working properly, then you have to make sure that the waste material from the human body is kind of removed. And if it's not naturally removed in the form of urine, then unfortunately people have to go through a dialysis option, where they're going and basically is essentially doing the function of what your kidneys would do, and remove the waste material from your blood, and then that is removed out, and then that's how you keep your body healthy. It's a very unfortunate and torturous process. I mean, just recently, 3 months ago, my father-in-law, he unfortunately passed away, and right before he passed away, he was given the option of doing a dialysis, and unfortunately, before we could make a decision, he passed away. But that was one of the things, that his kidneys had started to fail. So very important that the dialysis option of how the kidney works and how it removes the impurities selectively, the waste material from the blood, without actually removing the good stuff from the blood, is what you would call as osmosis. Okay, so that's kind of the chapter objective. Okay, so let's delve right into it. Not going through every single thing, but some of it is pretty repetitive. Solutions can be defined as a homogeneous mixture of two or more substances, okay? But specifically when you add sodium chloride, which is common salt, in water, so the salt becomes the solute, the water becomes the solvent, and the mixture is called as the solution, which would be your salt solution. Okay. If you have ever gone to Walgreens and if you have filled a prescription which is mostly liquid-ish in a bottle, or like a very common one, if you have ever been, this is one of the most common one, amoxicillin. You guys ever had to have this one? It's an antibiotic.
Yep. Yep.
So if you guys go to the Walgreens, the pharmacist is basically taking a stock solution which is extremely concentrated, and then they're diluting it to the prescription strength that your doctor has prescribed. If your doctor thinks that you have an extremely high bacterial load, they're going to give you a higher strength prescription. If you're going to have a milder case of bacterial infection, they're not going to give you the higher strength prescription. It is basically a lower strength prescription, right? But what are they changing? They're basically changing the concentration. The pharmacist has got access to the stock solution, which is essentially the neat thing that they get from the pharmaceutical company. And the reason why they make it extremely high concentration is because it's easy to transport. You don't want to be, if you're transporting, like if you're transporting a, okay, so they're like, so the doctor, as a prescription, he's having patient A and patient B. Okay, one of them is having a prescription for 5% strength. The other person is having 2% strength. The pharmacy, on the other hand, they're going to be having an 80% solution. 80% means 80% is the solvent and 20% is the water. In this case, 5% is the medicine, or what you would call as, no, not solvent. This would be the solute. So this is the solute, which is the medicine, and then 95% parts is water, right? So it's not practical for the pharmacist to be supplying the medicine in the right ratio that patient A, because the pharmacist doesn't know what is the concentration. For all you know, there could be a scenario where someone is getting 10% strength, right? So what they do is, that's why it's a controlled drug, right? It goes to the pharmacist, the pharmacy could, oh, okay. The pharmacist controls the concentration. They get the 80% strength, and then they're diluting it to 5 to 10%, whatever they want, because now they can control and fill in the prescription as per the needs of the patient. The other reason is, from a commercial standpoint, hopefully you guys understand that at 80% strength, it's a lot more easier. Now you're not paying to transport water. It's a lot more easier for the pharmacist to dilute it to the required strength as against the pharmacist or the manufacturer sending the chemicals at a lower concentration, because now they're paying for the transportation of water, which is unnecessary money, right? They really want to pay money for transporting the medicine, which is the 80%. So there is a application benefit of it, and then there is also a commercial benefit of it. Okay. Mixtures. So we looked at several of these things. Heterogeneous means similar, dissimilar. And this means similar. Okay. Seawater is largely composed of sodium chloride and water. A mixture can be anything, right? We have already talked about all these things. A solution is kind of a specific kind of a mixture. Heterogeneous and homogeneous. This is the definition: uniform composition throughout the sample. And one does not have it and the other one has it. A solution is a homogeneous mixture that contains small particles. Liquid solutions are transparent, blah, blah, blah. A coffee of hot coffee, vinegar, gasoline are transparent solutions. Okay. Air is a solution of gases, but technically air is a mixture of gases. If you have ever had a dental filling from the dentist that has got liquid mercury in solid silver, so the silver implant that has got the liquid mercury, and now if you go, this used to be a trend back in the 80s, 90s, and the turn of the century, but then mercury, as you guys know, is very toxic, and then research indicated that now instead of using mercury as the filling material, because again, if you go back to Mercury is one of the rare metals. It's the only liquid metal, first of all, okay, because metals are usually solid, but mercury has got some excellent physical properties that makes it a perfect candidate for dental filling. But mercury is toxic. As long as that mercury is contained within the solid silver, life is good. But unfortunately, if something happens to the silver, the solid silver inside which the mercury is encased, then it can directly kill that individual or make them extremely sick, right? So that's why we started going into composites, which is nothing but a ceramic filling. This is again a very complicated chemical compound, but thankfully they have done research enough on this, and it is non-poisonous or non-toxic to the human body. It kind of does the same job, and not only that, it is also cheaper. So if you look at the one generation before us, I mean, my father, my mother, my grandparents, I mean, many of them have tooth fillings that are still containing the mercury. But now if you go to a dentist, you would rarely even get the option of doing mercury. Okay. IV solution or saline solution is nothing but sodium chloride in liquid water. So if you have ever had a very bad case of throwing up or vomiting and nausea, what the doctor does is, I mean, since you need those essential minerals in your body and you cannot lose water, but some people have had this problem, they cannot even keep water down. And if you're continuously throwing up because of whatever reason, stomach upset or any other case of sickness that you're not able to take it orally, then since you're not able to keep water, and what is very critical for the functionality of the body and the salts, that's why they give a saline solution. And saline solution is nothing but sodium chloride in liquid water, which can be life-saving. Okay, so we looked at all of these. Okay, so then we have kind of looked at it. When two substances form a solution, the substance present in the lesser amount, or in other words, the one that is getting dissolved is called as the solute. The substance present in a larger amount, or one that dissolves the other one, the former, is called as the solvent. Together, they are called as solution. So solute plus solvent gives you solution. Okay. And generally, when this is a gas and a gas, this becomes a mixture. When it is a solid and a solid, it becomes a mixture. An ideal case of a solution that we can normally relate it is solid in liquid. So this is a solution. A liquid in liquid is a solution, and a gas in a liquid is also a solution. If the liquid is water, then it is called as an aqueous solution. The aqueous solution comes from the word aqua, which is the direct synonym for water. Okay. Solution can be, this is, okay. So very high level, colloids in suspensions are mixture that contains larger particles than particles in a solution. We're not going to get into the technical aspect of it. There is a little thing here, just for you guys' awareness. So if the mixture is called as a solution when the particle size is 1 nanometer. 1 nanometer is nothing but 10 to the power -9 meters. It's extremely small. Okay. Settling means you take a murky mixed solution. For example, you take some sand, okay, or take some dirt from your backyard or front yard, okay, and put it into a glass of water, okay. Stir it nicely with a spoon or something like that and allow it to settle, right? You will see that the particles settle down pretty quickly, correct? So that would be the category of what you would call as a suspension mixture. The components can be separated by filtration or centrifugation, okay? Centrifugation, if you are not familiar with it, you take something, a mixture, okay, and they do this. If you have ever gone to Quest Diagnostics, or what's the other one, LabCorp, some of those lab work, when you give a blood sample, what they do is they usually put it in a tube and then they kind of spin it at high speed, and that centrifugal force separates all the solids to the side and then makes it settle down to the bottom, okay? So that's the concept of centrifugation. Filtration is nothing but a physical medium. The pore size is small enough that you can actually separate out the solids. It's nothing but sieving, correct? So if you can settle out the particles either through filtration, centrifugation, or simply through settling, allow it to just sit down and the heavier particles settle down, that is called as suspension. If you cannot separate out the solid from the liquid, it is called as a solution because the components cannot be separated. A colloid, on the other hand, cannot be separated by common filtration techniques, and physically the size lies somewhere between 1 nanometer and 1 micrometer. So this is 10 to the power -9 to 10 to the power -6. And 10 to the power -6 is actually the larger number here, because this is 1 to the power 10 to the power 9 to 1 to the power 10 to the power 6. So this is million. So anything that is divided by a smaller number is actually the overall larger number, mathematically. And then suspension is nothing but greater than 10 to the power -6. Again, these are just some scientific ways of describing what is the difference between solution, colloid, and suspension. We're not going to get into it. I just wanted you guys to be generally aware of it. Okay, questions?
Nope.
Yeah, none for me. I'm good.
Okay, cool. Electrolytes and non-electrolytes. We talked about a substance that conducts an electric current and water is called as electrolyte. The one that does not conduct an electric current is called as a non-electrolyte. Okay. Again, the principle is ions, which is going back to the ionic compounds concept. So sodium chloride is in solution. So basically a salt solution versus an aqueous solution of hydrogen peroxide. Hydrogen peroxide, we have all used this. Hydrogen peroxide is a covalent compound. These are ionic compound. So when you have two solutions, this has got H2O2 plus water. Please note the difference. It's H2O2, which is hydrogen peroxide. This is the disinfectant. This is, of course, water. And the second one is NaCl plus water. Okay. So which one do you think will conduct electricity in this in between these two?
The one with NaCl in it.
Correct. So this is the electrolyte. This is the non-electrolyte. And the reason for that is simply because the sodium ions plus the chlorine ions is bond, and as a result, it conducts electricity. Okay, so electrolyte and non-electrolyte. Okay, what else do we want to see? Okay, so strong electrolyte, of course, it's ions, conducts an electric current. NaCl, KOH, HCl, basically anything that is ionic compounds. You guys know how to define that. Chapter 3. There are some which are weak electrolytes, so they are not as good as some of the ionic compounds, but there are exceptions in chemistry like ammonia, hydrogen fluoride, all these things which partially conducts electrolytes. So if you put them in water, it will not give you a very strong electrical path. It will be somewhat of a weak one, but there is still enough. I mean, like it will be like 1 milliamp to say 100 milliamp. Whereas in an ionic compound, you're looking at amps. And 1 milli means 10 to the power negative 3. Okay. And then non-electrolyte, we just looked at it. That's purely most of the covalent compounds. Okay. Let's see if we want to do all these things here. I'll just check something. Okay, so let's zip through this real quick. It's just a simple concept. I want to spend too much time into it. This is again tracking the equivalence. Okay, an equivalent is the number of moles of charge that a mole of ions contribute to a solution. Okay, so now you're trying to just charge attract the equivalent charge. Okay, and go back to your basic ionic compounds chapter. You know that potassium has got 1 positive charge, calcium has got 2 positive charge, aluminum has got 3 positive charge, sulfide has got 2 negative charge, nitrate has got 2 negative charge, oxygen has got 2 negative charge, so on and so forth. So table 3. Okay, so look at these. So look at the positive charge, a single. Here you have 2 plus, here you have 1, here you have 3 minus. Okay, so now you are trying to track the equivalent charge per mole of the solution. Okay, so let's look at an example. How many equivalents of sulfate is present in a solution that contains 3.2 moles of SO4 negative 2 minus, the sulfate ions? Okay, so you know that each sulfate has got a 2 negative charge. So if you are having 3.2 moles of that, you're simply doing 3.2 moles of sulfate ions is what you have present, but each of the sulfate ion contributes to equivalent charge. So simply it is 3.2 times 2 or 6.4. So it's not a very complicated concept. Just look at the number of negative or positive charge. So each mole is contributing those many charges, 1, 2, or 3 positive, negative. So 3.2 or X number of moles will simply be a multiplication of that. So sometimes you're simply doing milli equivalent, and milli equivalent is nothing but 1000 milli equivalent is equal to 1 equivalent. For example, if an IV solution of NaCl contains 154 milli-equivalent of sodium positive ions, sodium is 1 positive, how many milli-equivalents of sodium positive ions is a patient given in 100 mL of the solution? Okay, so 154 milli-equivalent is present in 1 liter. Okay, so you have 800 milliliters. So it's all a conversion game. So this becomes 0.8 liters because 800 milliliters is nothing but 800 divided by 1000. So that gives you 0.8 liters. So you have 154 milli-equivalents per liter, but you have only 0.8 liters. Letters get cancelled. Multiply 154 by 0.8, whatever that number is. That is the milli-equivalents of sodium positive ions in that milliliters of solution. Okay. And now you have to make sure, because they're asking you Na plus. Thankfully, Na plus has just got 1 positive ion, so you should be okay. If the same question would have been calcium, which is Ca++, and this becomes CaCl2, the approach would have been exactly the same: 154 milli-equivalent per liter times 0.8 liters. Let's get cancelled. So 154 times 0.8 is equal to 123. Okay, but this is milli-equivalent. But since calcium has got 2 positive charge, don't forget to multiply it by 2. The answer becomes 246 milli-equivalent of calcium. And the problem that you have, it is 123 milli-equivalent of sodium positive, 1 positive charge. You see the difference between the two examples?
Yeah, a little.
Okay. Brian?
Yeah, I think so.
All right. So want to get to okay. Let's see, solution, similarity. We're going to do all these things on Thursday. I want to see what is a good breaking point here. All right, so let's go a little bit more here. Okay, solubility. Let's look at it from a very high level standpoint. You guys didn't sound very convincing about the equivalent. Do you want me to repeat that?
No. We can just rewatch it.
Yeah. I can repeat it. I mean, I'd rather make sure that you guys understand this concept. You guys don't, or is it just simple tiredness at this point?
I get it. I gotta be the one to move the pencil. I'm just following along with you.
Okay.
So
Okay.
I'm sure once I get into my homework, it'll I'll be able to wrap around my head.
Okay, cool. All right, that's good to know. Okay, Brian, how are you feeling?
Yeah, I'm in the same boat. This is a good like baseline for me to understand it, but once I start getting into doing the practical stuff with the homework, it'll more than likely click better, like most of this stuff has.
Okay, great. Okay, thanks. Okay, so yeah, so then that gives me the confidence. Okay, because I want to try to get to a certain point before I close it out for tonight. Okay, solubility. Okay, solubility is basically, we talked about, is the amount of solute that dissolves in a given amount of solvent. Okay. Tanisha. Okay. So it's usually reported in grams of solute per 100 milliliters of solution. So take 10 grams of sugar, okay? You put it in 100 ml of the solution, okay? It's 100 milliliters of the solution, okay? Now, what you're going to see that, so now the solubility is nothing but 10 grams divided by 100 milliliters, multiply that by 1000 milliliters, or no, I would not to multiply it by, it's actually divide that by 1000 milliliters to express it in liters. So 10 grams divided by 0.1 liters, you can say that this is 100 grams per liter. Okay, that's the solubility. Let me ask you a simple solution, or a simple situation here. Okay, you keep on adding salt to this solution that has already got, keep on adding sugar to this solution, okay? What do you think is going to happen?
I mean, eventually the water is not going to be able to dissolve the sugar.
And why is that?
It's I remember from high school, it's called a supersaturate. It's the point where water can no longer absorb or dissolve the sugar.
Yep, exactly.
Yeah.
So you're absolutely right. You're saturated, right? Like, you know, let's take this example. I'm kind of trying to teach you a concept. You're tired. You're kind of, okay, I'll sit through it. I'm tired. It's not making sense. A point will come where you guys are just going to tune me out, correct? And like, dude, I'm done. You can tell me whatever you want, but it's not going to stick with me, right? That is what you would call as the point of saturation, okay? So a saturation solution means that you cannot add any more solute to the solution, and it basically remains undissolved in that solution. That's why a point will come when you try to add it, it will simply settle down. It will not get dissolved in the solution. And the maximum ability of every solution has got a saturation value. If your concentration is going to be less than that saturation value, then it is called unsaturated. If your concentration has reached that saturation value, of course, it is called as state of saturation. So that's the basic concept, okay? Then let's see, what else do we want to do here? So there's some technical things here. I'm just trying to cherry pick some of these things which are relevant. So sodium chloride dissolving in water, you know this, and this is true even for salt solution. It's actually one of the simplest experiments you can do it at home. Keep on adding salt to this thing, use a stirrer, and you do know that when you're stirring it, right? You're mixing it, and when you're mixing it, you're providing energy, correct? You guys agree with that?
Yep.
Mm-hmm.
Okay. So what I'm trying to say is that by providing energy, you can actually increase the thing. So if you have a salt that you're adding in a unmixed solution, and try this experiment. It's actually very easy. You need 2 glasses. One of them, you don't stir it, you don't mix it. You will see the salt will eventually over time dissolve in it. Like if you add 1 tablespoon, it'll kind of form a small layer here. You give it enough time and that salt will kind of mix into the water. And that is through what you would call as dispersion. We're not going to get into all these technical things, okay? But it will get into the water. You're accelerating that process. So if you add the same one teaspoon of salt into this and then you mix it, now you're providing energy and then driving that solute, the solid particles of salt, into the water, okay? So this is, now you're driving it and increasing the solubility of that solute, which is the salt in the water. The other way you can do it, and then keep on doing it, and you will be able to continue doing this until you, and I'm talking, you're continuously stirring or mixing it, okay? So you can keep on adding 1 teaspoon, 2 teaspoon, 3 teaspoon, 4 teaspoon, and a point will come where then even after stirring it, you will realize that you have reached the saturation point for that water, the quantity of water which is the maximum allowable solute it can absorb and dissolve in it. And then it does not matter whether you're stirring it, you're giving it enough time, the salt will simply settle to the bottom because you have reached the point of saturation. Okay. Now, the third point is, now if you want to increase the solubility, because now you have reached the point of saturation, start applying heat from the bottom. When you heat it up, you will start seeing that even at the point of saturation, now more salt can be added into the solution. This is exactly what happens when you're cooking. The salt or the sugar that you add, eventually you increase the solubility by the solubility increases when you increase the temperature. And similarly, the solubility decreases when you decrease the temperature. Okay, a classic example is oxygen in water. Now, you and I, we are not aquatic species like fish, which have got gills. Okay, so you imagine these fish which have got these gills, which are their means of respiring. They don't have a nose and they don't have lungs like us, but they do have gills. Okay, the concept is the same. Fish living in a water body, they require the oxygen for survival. What happens is, in a normal summer temperature, when the ambient temperature is high, the water quantity is the same. Okay, this water quantity has the ability to accommodate a certain concentration of oxygen in the summer. In the winter, because the temperature drops down, the solubility of oxygen in water, what we call as DO, or dissolved oxygen, goes down. And that means in the same quantity of water in the lake or in the stream or in the river, your ability of the water to carry dissolved oxygen, which is very vital for the fish and other microorganisms to be breathing, that goes down. And as a result, you see a higher population of fish not surviving the winter. It's a simple case of the water not being able to have enough oxygen in the dissolved phase. Okay. We're in here, so I'm not going to go into all these things. Okay. So exothermic, endothermic, basic principle. Where is this? Okay, not going to go into all of these ones. If you see a homework, something that talks about this dipole and pole and this polar, I mean, I would just skip it. I mean, because it's not that critical that we understand this concept. I'm really trying to see the effects of temperature and pressure. That's what. So you guys understand the basic concept of solubility. What is the ability of a certain substance, in this case, the solute in water? Okay, so that's the concept of solubility. And what is the effect of temperature and pressure? So we just looked at the effect of temperature, and now we're going to look into the effect of pressure. So both temperature and pressure can affect solubility. For most ionic and molecular solids, solubility generally increases as temperature increases. Okay, a classic example is sugar. Sugar is much more soluble in a cup of hot water than in a glass of iced tea. We have all done this, right? So this is your coffee mug. Add some sugar to it, 1 teaspoon. Try doing the same thing in iced tea. Which one dissolves quicker?
The coffee.
Correct, because it's at a higher temperature. So as temperature increases, solubility increases. The sugar is not dissolving in the coffee because it's coffee, and the sugar is not dissolving in the iced tea because it's tea. The tea and the coffee doesn't really have much of a role to play in this. It's the temperature. So in an iced environment, the solubility goes down, and that's why you have to what do you call? Add a lot more energy. That's why when you're making an iced tea drink, I always recommend that you put the sugar in normal temperature water first, dissolve it, and then add the ice cubes, as against taking an ice cube and putting it into the water and chilling your drink. Now adding the sugar, you're going to have to stir it a lot more compared to doing it the other way around. Try it. Okay, so that's the question of temperature effect. On the other hand, so that works for solid, okay? But when you remember solution, right? Solubility is only applicable for solution. How much solute dissolves in a solution? Okay, now salt and sugar are solids. We also saw that a solute can be a gas. So what happens when you have a gas in a liquid? So okay, I was incorrect in that example of the fish. I apologize. The fish and the dissolved oxygen example, that's actually incorrect. So gases, the solubility of a gas decreases as the temperature increases. Okay, so if you increase the temperature, the solubility of gas decreases, which means that in the summertime, there is actually a lower dissolved oxygen in the streams. Okay, and the reason for that is because increasing the temperature increases the kinetic energy. So you know that the gas molecules are like spread all over, right? So these are the gas molecules. So when you increase the temperature, these gas molecules are now occupying a much larger space. So what that means is they have a tendency to go from the liquid phase into the gaseous phase. So if you have a receiving, not a receiving stream, but if you have a river here, and in the summer, when the temperature increases, the gas molecules are actually escaping from the liquid into the gas phase. So, and now when I'm talking gas, I'm talking oxygen, right? So oxygen dissolved in water is called as dissolved oxygen, which is what is necessary for survival of the marine life. So now if these oxygen molecules are escaping the liquid phase, your oxygen concentration goes down. And as a result, that is what is detrimental to the marine life. I apologize, I had this backwards in the previous example. So the solubility of solid increases as you increase the temperature. The example to remember there is salt solution and sugar solution. Both of them, the solute is a solid, right? But when it comes to gas, which can also be a solute, the solubility of that gases or the solute decreases as you increase the temperature. Okay. Questions on that? Sorry about that confusion.
No, that makes better sense. I'm glad we
Yeah.
clarified that, because I'm like, what?
Okay. Yeah, on that one. Glad that we came through that slide. Okay. Pressure changes. So pressure changes do not affect the solubility of liquids and solids. For example, you take a gas, sorry, not a gas. You take a solid, which can be salt or sugar, right? You add it into water, and then you have a piston and you try to press it. Okay, you will find out that the solubility in this case, whereas you have the same thing and now you are pressurized. So this is P2, this is P1, P2 is greater than P1. Okay, so the solution in the second case is at a higher pressure. You will see that the pressure is not having any effect in the solubility of a solid or a liquid. So it's not that by pressurizing it, you can have more salt into the solution. okay? But when it comes to gas, okay, and you're trying to put some gas into a solution, okay, you will see that the pressure has a significant effect on the solubility of how much gas you can put it into the solution. And this association is described by Henry's law. Okay, and what Henry's law says that the solubility of a gas in a liquid is proportional to the partial pressure of the gas above the liquid. Let's look at an example here. So higher the pressure, higher the solubility of a gas in a solvent. Okay, so what this is saying is, as you increase the pressure, the solubility increases. And this is only true for gases. For liquids and solids, as you increase the pressure, the solubility remains unchanged. It doesn't go up, it doesn't go down. So practical application of Henry's law is carbonated soft drinks. So soft drinks, you know, is nothing but carbon dioxide, which is the carbonic acid that is there. The fizz that comes out when you open a soda pop is basically carbon dioxide. It's carbonated drink. You guys all know that, right? So when it is pressurized, whether you are using a bottle or a can, you know that it has got a higher pressure. That's why when you shake it up and then you open, you know, we've all done this as a kid, right? We've done that to our siblings, we've done that to our friends, and gotten scolding from our parents. But you understand what I'm saying, right? It's already under pressure. And then what you do is when you open up that thing, you're just releasing all of that pented up gas inside that soda container. Because the atmospheric pressure is 1 atmosphere, as you guys know, the atmospheric pressure. And now everything that the can has got a much higher pressure. So it's probably somewhere between 5 and 10 atmospheres. And then when you pop open that little tab over there, now you're allowing it to come to 1 atmosphere. So that's why everything just comes out. Okay. And you also know that eventually when you pop open a bottle of can, even when you don't shake it and then you just leave it on the counter for about half an hour, eventually all of that fizz, which is nothing but carbon dioxide in the form of gas, comes out, and that's why the soda goes flat, which most people don't like. We really enjoy that fizz drink. Same thing with beer. Beer can go flat, carbonated drinks can go flat, your seltzers can go flat. You know, anything that has got the carbon dioxide, or your plain, what do you call those drinks? I'm forgetting the word. Just the carbon dioxide and water. What do you call that drink? Some people like it.
Carbonated soda, or
no, not soda, but just water, right? I mean, some people like that fizz without any flavor to it.
Are you just talking about sparkling water?
Oh yes.
Thank you. That's all I was looking for, sparkling water. Right. So again, I mean, it's the same thing, right? And that's why 1 liter thing, unless you have a big party, you don't want, I mean, like if you're just drinking a soda or something like that by yourself, most people don't like to keep that 1 liter bottle, even though it's cheaper, right? Unless you have a party, because if you don't use it, you can try closing that seal as much as you want. But you and I, we both know that sitting in the refrigerator for 1 day, the soda is eventually, the carbon dioxide is escaping, right? Because it's just not the same as what it comes factory sealed. Okay, so chemistry standpoint, closed can of soda, your root beer, higher concentration of carbon dioxide in solution as indicated by the left one, lower pressure of carbon dioxide, lower concentration of carbon dioxide in the solution. So the lower pressure of carbon dioxide in the air is called as partial pressure, and lower concentration is called as solubility. And Henry's law basically says that the solubility is directly proportional to the partial pressure of that gas in the vapor phase. So partial pressure is a vapor or gas concept. This one is a liquid concept. The gas is still the same, carbon dioxide. Make sense?
Yeah.
Cool. Another example, scuba diving. If you guys have ever experienced scuba diving, increasing. So as you go down, so this is your surface of the beach. Scuba diving, you're kind of going down, and as you go down, you're increasing the pressure, correct? Because of that, when you are going down and down, what's happening is that there is oxygen and nitrogen in air, and human beings are taking in both oxygen and nitrogen. It's not that we are selectively screening out the nitrogen is there also. What happens is, because more nitrogen is dissolved in the blood under the higher pressures, you want to make sure that, especially when you're going diving, you don't want to have the formation of nitrogen in the form of bubbles in your joints and the small blood vessels, because the solubility of the gas in the diver's blood slowly increases or slowly decreases as you go up. As the pressure decreases, the solubility decreases. As the pressure increases, the solubility increases. Okay, so when you go down to that lower level, that's good, right? Because nitrogen and oxygen are reach that state of equilibrium. But then once you start coming up and the solubility decreases, you want to release that nitrogen from your blood in a very small, controlled fashion. Otherwise, you can form bubbles in your joints and small blood vessels, and that can be pretty painful. I don't know if you have ever experienced, I don't do scuba diving, but I have heard from some people that if you come too fast to the top, that nitrogen, as the solubility decreases and it's starting to bubble out from your blood, you don't want it to be trapped in your muscular joints and in the blood vessels, because then it can be extremely painful. Because now, instead of the blood traveling through the blood vessels to your arteries and your veins, now you're having a nitrogen bubble. If things get really out of control, that nitrogen can create a block, and then you can actually cut off your oxygen supply, which is a really bad thing.
Yeah, the bends it sucks.
Yep. Are you a scuba diver?
I used to be when I lived in California. Made that mistake once. Luckily, it wasn't too bad. But yeah, it's rough.
Yep. So there you go. Thanks for that personal validation. Cool. Okay, any questions?
None for me.
Nope.
You're good. Okay. So why don't we stop here? And I want to have a clean break for the next topic, which is, this is where I want some of this, as you guys saw, I deliberately went fast because not all of it is, it's more theoretical. I wanted to kind of start getting into some practical application, which is what we're going to be focused on the bulk of Thursday, which is going to be on concentration. We have already looked at it. I mean, now we are just going to be going through different ways of expressing concentration. I'll kind of give you a sneak peek. One of them is how much weight of the solute is there in the given volume of the solution. Okay, that's one way to express the concept of concentration. Before you come on class, I want you to pick up a bottle of Tums, or not Tums. What's that pink thing that we all like to drink when we have stomach upset?
Oh, Pepto-Bismol.
So,
Thank you, Pepto-Bismol. So that's, if any of you guys have something like Pepto-Bismol or a cough syrup or something like that, I want you guys to go into that label, and I want you to look at this W/V, okay, just to kind of get exposed. All you're looking is for the active ingredient. The concentration expressed is weight over volume. And what that means is you have 5 parts of that active ingredient in Pepto-Bismol, that is basically that active ingredient of whatever that chemical is, in 100 milliliters of solution. That's what is the concentration of Pepto-Bismol or your cough syrup. Okay, so this is one way of expressing weight over volume. The second one is volume over volume. Okay, so the first one, weight over volume, is usually for both solids and liquids dissolved in liquids. But when the solute is a liquid, okay, then you can use weight over volume, but more typical common way of expressing that concentration is how much volume of that solute is there in the volume of the solution. Okay, and then you multiply it by 100% to express it as a concentration. A great example is phenol solution. Okay, so I want you to look at your medicine cabinet and see if you have any of these things. These are usually only working for a solution, okay, because the bottom line is it has to be a solution. So you need a water in the denominator. Okay, so this is one of them. And then there are other ways of expressing some of these things, which are just kind of giving you a sneak peek, and then we'll kind of go into it in detail on Thursday. Parts per million. You must have heard of these things. These are how many parts of a substance is there in 1 million parts. These are generally used for extremely small concentration. Usually it is used extensively in air pollution situations. So you have 30 ppm, which means that you have 30 ppm of, say, carbon dioxide. So you have 30 parts of carbon dioxide over 1 million parts of air. Okay, so this is another way of expressing concentration. And then the last one, I believe, is molarity, which is the one that you already know. It is the number of moles of a substance in 1 liter of solution. So we're going to look at some examples of how these 4 concentration units are going to be expressed. And then we are going to be learning about one important concept, and that will be hopefully the last topic I want to cover in this one. And then we'll see if we have time, we'll do some of the other concepts, but this is the dilution, where the molarity times the volume is again a constant, just like what we had learned in the gas laws. And this just means that M1V1 is equal to M2V2, or C1V1 is equal to C2V2. So you have condition 1 and condition 2. So the product of the concentration times the volume of that solution is always going to be a constant. In other words, you have a low concentration and a high volume is the same as a high concentration times a low volume. And we're going to be using this to calculate different concentration given C1, V1, and C2, or V1, C2, and V2. So 3 out of the 4 are known. We're going to calculate the 4th one. So those are the 2 main concepts we'll learn on Thursday, and we'll try to wrap up this chapter. And if time permits, we'll kind of go into some practical applications, at least zip through it at a very high level. But this is where the bulk of the focus is going to be on Thursday. Okay, that's all I have for tonight. If you guys have any questions, you know how to get hold of me. Are we good for tonight?
Yep, sounds good.
All good.
Okay. And Brian, unlike most days, I will not see you in 1.5 hours.
Yeah, I gotta get the rest of the night off.
Yes, you do. The same thing on Thursday also. We are not having a class on Thursday for math. Drew, I'll see you guys. Drew and Brian, I'll see you next Thursday at 5:30.
Sounds good.
Have a good
Have
night.
a good
Take
one.
care, guys.
Yep.
Good night.